Hello, so physics 20s. I just want to explain the difference between what we're calling true weight and apparent weight. And so here I've added a couple of things already. Uh, Gravitational field strength, it, as you may have seen in that video, it does vary depending on where you're at. It's actually, the gravitational field strength is greater at the North Pole than it is at the equator because the Earth is bulging as it spins, which we always think of the Earth as a perfect sphere, but it actually isn't. So that's why uh, there's a slight increase in the force of gravity the at the North Pole. If you can imagine the Earth looking like more of a like an oblong shape like this, okay? And if you're at the North Pole, the distance between you and the center of the Earth is less there than it is if you look. It's almost, this is more of an ellipse when you go towards the equator. So that distance there is longer than this distance here, which means that the force of gravity is stronger at the North Pole. And there's other variations too in terms of the density of the Earth's core, or not the Earth's core, but the mantle of the Earth. That can vary a little bit. So that's something fun to mention. What I want you to know here, though, are these definitions between what's called true weight and apparent weight. So let's just go through those. True weight is the easy one. It's just the measure of the gravitational force acting on a mass. And I added at a point in space. The true weight is just calculated as how we've always calculated weight, is the mass of the object times whatever g happens to be at that location. Okay. Apparent weight, though, is different. And this first definition may not make a lot of sense, but it says it's the negative of the normal force acting on a mass. The normal force acting on a mass. Well, we'll look at that in just a second. I like to think of apparent weight as this here, and I already wrote it out for you. It's really a measure of how heavy you feel when you're experiencing a net force. So the the classic example, and I did post a video of that, is riding in an elevator. If you put a bathroom scale on the floor of an elevator and stand on it, before you go up or down, it will read essentially your true weight. But when the elevator goes up initially, if you're going up, you'll feel a little bit heavier because the floor is moving up against your body and your body senses that. And so you kind of feel like, oh, you feel a little heavier going up. So your apparent weight actually increases if you're accelerating up in an elevator, and just the reverse happens if you're going down. So if you're on, like, the 10th floor or something and you're making your way down, initially the scale will read your true weight, but then as soon as the elevator starts to accelerate, like, the first second or two, you'll feel like the floor is kind of being moved out from underneath you. You get little butterflies in your stomach, and you feel lighter. That is your apparent weight. It's how you feel based on um, the fact that you're accelerating. So what does that look like if we sketched it? Let's just look at this here. So if we are standing in an elevator, okay, so here's our elevator, and if we're standing in the elevator, we will experience the force of gravity. So I'll show that just like this. The force of gravity is always straight down, and that's depicted like that. And the floor of the elevator exerts a force up on you. And I'm going to draw this one a lot bigger for starters because we're going to assume that you're moving up in the elevator to start with. So the the floor of the elevator matches gravity, but then it also has to push even harder than gravity because the whole elevator is accelerating upwards. So what we now have here, and this is how you would analyze an apparent weight question, is now we have a net force because the normal force up is greater than the force of gravity, and so we could actually write it like this. Now, obviously the force of gravity would be down and the normal force would be up. But we can account for that in breaking down these questions, because really the net force would also be up in this case. Okay, but let's just expand this to start with. So what we'll say, and I know we're adding the force of gravity and the normal force as vectors, like one would be negative, one would be positive. But let's just break them down initially. Oh, actually, wait, we could do it a little simpler if we just start doing that. So the net force will be the total mass times the net acceleration. The force of gravity will be m times g. And the normal force, well, we'll just leave that as the normal force. We really don't have we always find it indirectly because it's proportional to gravity most of the time. But anyway, so the apparent weight is really the negative of the normal force. This is where we get our apparent weight from. So we have to solve for it. So to do that, I would subtract mg from both sides. And now I get an expression that looks like this: ma net minus mg equals Fn. And there's a way to kind of simplify this if you want. You can add this one to your formula sheet. We can factor out those m's. I know we don't do that a lot in physics, but it sure is helpful if you remember that from your other math classes. Let's factor out the m. So now the expression looks like this: m times a net minus g equals Fn. And when we do this, it will give us the magnitude of the normal force, in this case up. But what you have to catch if you're solving for apparent weight is that as it shows in this expression right here, apparent weight is equal to the negative of the normal force. It does show it's equal to the force of gravity in this expression, but that's if we're not moving. So to get your answers for net or apparent weight, which I'm going to post some of those shortly, but you can use this expression here. And when you do it, you should account for the fact that gravity is negative. So you'll really be subtracting a negative 9.81 if we're on the surface of the Earth, which we're going to be for most of these. So effectively, you're going to be taking the net acceleration, you're going to be adding, you subtract a negative, you're going to be adding 9.81 to that, but then you can solve for the normal force, and then all you have to say, well, the apparent rate is always going to be down. So the apparent weight is the negative of the normal force. You'll feel heavier downward. That's kind of the idea. So anyway, refer back to this as you get into any questions. There won't be a lot of them, but there will be an occasional question that asks you to deal with a true weight and apparent weight. Again, the true weight one is the easy one. That's just the force of gravity acting on the mass at a point in space. Apparent weight is how heavy you may feel because of the fact that you're accelerating. So you'll either feel heavier or lighter, depending on if you're accelerating up or down in an elevator, if that helps. So anyway, look for the further review sheets as we keep going, but keep up the good work.